All right, so let's start with sort of a recap of the series tests we've done so far. Right, the first one we had done was a geometric series. So if you can identify something as a geometric series, that makes it real easy. Ratio is less than 1, absolute value, it converges. Bigger than 1, it diverges. All right, then we had looked at the divergence test, or what I sometimes call the nth term test. If the limit is not equal to 0, then the series diverges. All right, from there we then looked at the integral test. If you can compare this to an integral and the integral converges, the series converges, diverges, it diverges. All right, the p-series test was pretty easy as long as it's a p-series, right? Between 0 and 1, including the 1, it diverges. Bigger than 1, it converges. All right, then we had looked at the direct comparison test. So we compared two series. If the smaller one converges, the smaller one diverges, the bigger one diverges. If the bigger one converges, the smaller one converges also. Right? We had looked at the root test, right? And again, the root test is like the p-series test in that it's easy, but it only works in certain cases. All right. There are other types of tests to look at too. So now from there, let's look at the limit comparison test. Okay, the limit comparison test is a test that will help us out in cases where direct comparison doesn't work. And so here's my little introduction. Suppose I looked at the sum from n equals 2 to infinity of 1 over n minus 1 squared. And you said, well, that is pretty close to a series of 1 over n squares, isn't it, right? I mean, that's only the little minus 1 is the only difference between 1 over n minus 1 squared and 1 over n squared. This thing I can identify pretty quickly as being a convergent p-series. So now how do these two things compare? How does 1 over n minus 1 squared compare to 1 over n squared? Well, this time as I subtract the numbers on the bottom, then the whole fraction ends up getting bigger. So it actually compares in that way. Well, does that help us? Just because the smaller one converges doesn't guarantee me anything about the larger one. The larger one might also converge, or it might diverge, right? The values might become infinite. So in this case, the direct comparison test fails me because even though I picked a nice series to compare it to, it's not strictly smaller than a convergent series. It's actually slightly larger than a convergent series. But here's the question. Are they close enough? In other words, does 1 over n squared behave very, very closely to 1 over n minus 1 squared, even though one might not be strictly larger or smaller than the other? And that's where the limit comparison test comes in. So the limit comparison test says, all right, compare the two functions together and see if they grow at the same rate. If they grow at the same rate, then we can use it as a comparison. So the limit comparison test says, do they grow at the same rate? If so, then maybe that 1 over n squared is a perfectly good comparison. So here's what we do. We've got two series, a sub n's and b sub n's, where the a sub n terms are greater than 0. The b sub n terms are also greater than 0. And we're going to look at the limit as n approaches infinity of the a sub n over the b sub n's. All right? And we're going to look to see if that is some value that is positive and finite. What I don't want is I don't want infinity or 0. So I don't want infinity or 0. Because if I get 0, that means that this term on the bottom is growing faster than the one on the top. If I get infinity, that means the one on the top is growing faster than the one on the bottom. If I get something, and it could be 4/5, it could be 12,000. As long as it's positive and it's finite, then that means the two of them are growing at the same rate. Then test your b sub n, right? So the a sub n is the one that I was given. The b sub n is the one that I come up with to use as a comparison. Question is it a good comparison? If it's a good comparison, then I should test that series to see what it does. Whatever one does, the other does. So if that's true, then the second part of this is if the b sub n converges, then the a sub n converges also. And then it's true for divergence also, right? If the b sub n diverges, then the a sub n diverges too. All right, let's go back to my example that I had with the 1 over n minus 1 squared. All right, so I'm going to look at the sum of all the 1 over n minus 1 squares, starting at 2 to infinity. Let's try the limit comparison test with 1 over n squared, right? So using the terminology above, this thing is my b sub n, that's my a sub n. You realize when you go to divide it, it doesn't matter what order you divide them in, because let's say you took the limit and you got a limit of 2. If you flip the fraction over, you get a limit of a half. So if you took something that was finite and flipped it, it would still be finite. So the order that you put them in actually doesn't matter. So let's look at the limit as n approaches infinity of 1 over n squared divided by 1 over n minus 1 squared. Right? So we invert and multiply, and we've got n minus 1 squared over n squared. If you wanted to, you could actually expand this out, right? You can make it the limit as n approaches infinity of n squared minus 2n plus 1 over n squared. L'Hopital it a couple times, and you'll get 1. Okay? That's my L value. That's part 1 of the problem. That's the hardest part of the problem. Okay, once I get that L value of 1, so the L equals 1 implies that what I've found is a good comparison. So my comparison is good. That's good. All right, so now test that b sub n function. This thing is easy. This is a convergent p-series. Whatever you compare it to should be that easy. Compare it to a geometric series, compare it to a p-series, compare it to something that's easy. If you start comparing these to something that's as complicated or more complicated than the original question, then this comparison test doesn't help. So the original series then, so here's my conclusion, the series of 1 over n minus 1 squared from n equals 2 to infinity converges by the limit comparison test and the p-series test. So this one is going to work a lot like the one that we just looked at, the direct comparison test, because you can't do it by itself. It's got to be along with something else. So if you have a limit comparison test, then you're going to also have to compare it to some other function and tell me what happens to that. All right, let's take a look at another one. You're going to start seeing a pattern of these pretty quickly, but we'll look at one that doesn't quite look as easy as the one that I had before. All right, so let's say I have this series from n equals 1 to infinity of the square root of n over n squared plus 1. Now, part of my issue here is that I don't know exactly how this behaves. Like I look at the n squared on the bottom and the square root of n on the top, and I say, well, what is the important part of this problem? The important part is the n to the 1/2 on top and the n squared on the bottom, so it looks like that simplifies to 1 over n to the 3/2. But who wants to sit there and go through and compare all different values of 1 over n to the 3/2 to see if it's strictly greater than or strictly less than this original blue function? So I'm going to use this as my comparison function, and I'm going to take a limit, and the limit comparison test I think will actually work a lot faster than me sitting there and comparing how 1 over n to the 3/2 compares to that original function. So let's run the limit comparison test. Let's take the limit as n approaches infinity of, you think I can do this all in one shot? I got the square root of n over n squared plus 1 divided by the green function, but dividing by the green function is the same thing as multiplying by the reciprocal of the green function. Okay, what does that give me? Well, this guy over here, that square root of n, is really n to the 1/2, so I got a case of same base add exponents. So 1/2 plus 3/2 is 4/2. 4/2 is 2. So I get an n squared on the top and n squared plus 1 on the bottom. Apply the limit as n goes to infinity, and I get 1. So what that means is that green function is a good comparison. That also means I'm about 92 1/3% of the way done with my problem. because I've got a good comparison that sum of all the 1 over n to the 3 halves from n equals 1 to infinity, that thing is a p-series with p greater than 1, therefore it converges. All right? So that thing converges by the limit comparison test and the p-series test. Okay, so again, just remind yourself what those L values mean when you come up with those limits. In the cases I did, I guess I came up with a couple of examples where those limits were both 1. Do they have to be 1? They don't, right? They could be 3/4, they could be 7/8. As long as they're positive and finite, we're good. All right, let's try one more example. And then we'll get into alternating series. So let's take a look at this one. I'm going to take the sum from n equals 1 to infinity of n times 2 to the n over 4n to the third plus 1. Now, I want to find out if this converges or diverges. You want to try some other method besides this, you can, right? But otherwise, you're going to have to integrate this, or you're going to have to try a direct comparison test and see if you can find a function that's strictly greater than or less than that works in the order that you want. It looks to me like the easiest thing might be to try a limit comparison test. So if I'm going to use a limit comparison test, I got to compare this to something that's easier to work with. Something that's easier to work with is not necessarily a simple looking function for this thing here, right? That 2 to the n is going to be there at the end anyway, right? There's nothing I can do with that 2 to the n. It doesn't cancel anything out. Look at the other important parts of the problem. I've got an n on the top and a 4n cubed on the bottom. So it looks like an n squared might be an appropriate denominator. Constants are negotiable. I'm going to leave that 4 on the outside there because I'm trying to make my comparison function as simple as possible, and so I'm going to leave out that 4. All right, is this a good comparison? Let's find out if it's a good comparison. Let's take the limit as n approaches infinity of one function divided by the other function. So I'm going to start with my n times 2 to the n over 4n to the third plus 1, and I'm going to multiply it by the reciprocal of the function I'm trying to test. Right, if it helps you to clean this up a little bit, let's leave our 2 to the n. Here I've got an n. Here I've got an n squared. N times n squared is n to the third. And then on the bottom, I've got a 2 to the n and a 4n to the third plus 1. All right, so those 2 to the n's are going to go away. If I now apply the limit as n approaches infinity, do you realize I get a quarter? All right, if you don't believe me, you've got the time, L'Hopital 3 times, and you'll still end up with a quarter. So that limit value is a quarter. Well, what does that mean? Is that good? Is that bad? It's good, right? Because the rule was it had to be positive and finite. Essentially, it could not be 0 or infinity. As long as it was not 0 and not infinity, we're okay. So that value is good. So now I've got to actually test the other one. So I've got to test the sum from n equals 1 to infinity of 2 to the n over n squared. Well, that doesn't look like anything that's terribly fun to do until you realize that one test that we have that's as easy as can be, the divergence test. All right, so take the limit as n approaches infinity of 2 to the n over n squared. And yeah, you can L'Hopital it a couple times. If you L'Hopital it a couple times, you realize that that 2 to the n far outstrips that n squared on the bottom. So this thing here, the important thing is that it's not 0. If it's not 0, it diverges. Remember that nth term test says as long as it's not 0, it diverges, but it can't tell me anything about converging. All right, so what's my conclusion? My conclusion is that original messy series diverges by the limit comparison test and the divergence test, or the nth term test. All right, I'm going to stop this one here, and I'm going to pick up alternating series on the next video. Give yourself a little break. Come back, we'll do alternating series, and then that's the last of the series tests.